Hello everyone, Mr. Newman here, and today we're going to learn about continuity and work some more with limits, and specifically one-sided limits. So let's get started. For number one here, just a reminder of what one-sided limits and how it works. This first one, we're asking for the limit as x approaches 2 from the left, remember that's what that symbol there means, from the negative side or from the left, of f of x, which f of x is this half of the circle here. So I'm looking at 2, make sure it's positive 2 and not negative 2. So I'm looking at that side from the left. As you get closer to positive 2 from the left, you're approaching 0. However, if we try to approach it from the right, it does not exist because it doesn't exist at all because there's nothing to the right of 2. And so the limit itself, the limit as x approaches 2 of f of x, does not exist because the limit from the left and the limit from the right are not equal. Moving on to number 2, you notice this is the absolute value function divided by the linear function. This is a parent function that we looked at before. Just a reminder, if you have a value greater than 0, then the output of that function is just going to be 1 because you're going to be having a positive number divided by a positive number. But if the output the input is negative, then your output is going to be -1 because you will have a positive value on top because absolute values are always positive, but you'll have a negative value in the bottom. So that's the graph of the function here, absolute value of x divided by x. Now that we have that sketch, it's going to be a lot easier to calculate all of number 2. So the limit does not exist because the limit from the left and the limit from the right, they're not equal. Well, let's evaluate those. Let's look at the next two. The limit from the left, that's going to be, as you're approaching from the left here, you can see the green arrow on the graph, that's going to be -1 because you're getting closer and closer to -1. The value from the right, you see the red arrow there, that's getting closer and closer to the output or the y value of 1. And so that limit is 1. So you can see the limit does not exist because limit from the left is -1 and limit from the right is +1. Let's do the same for number 3. Let's sketch it. And there are two ways to think about this. The way I like to think about it is a transformation of the above parent function. Since every x has a -2 behind it, that means that the input was shifted. So this is a left or right shift. And remember, the input does the opposite of what you expect. So I'd expect minus to go left, but we're going to go to the right. So this moves that same graph right too. You can also think of it as when you try to substitute a 2 in or evaluate 2, that's the value that doesn't exist. And so you notice this graph looks the exact same as the previous one, it's just shifted 2 to the right. So let's first evaluate this on the left side of the x value of 2. If you're approaching from the left, you're getting closer and closer to -1. If you're approaching from the right, however, you're getting closer and closer to 1. And so the limit does not exist because the limit from the left is not equal to the limit from the right. All right, moving on for number 4. Here we have a piecewise function, so the limit from the left, you see how it's a minus there. We need to think about, that means when x is less than 1. If x is less than 1, I can look at my piecewise function and I see that that's going to be the top function because that's where x is less than or equal to 1. So it's going to include where x is less than 1. So I can actually evaluate this simply by plugging 1 into the top part of the piecewise function. And that gives us 1. For the right side, I need to think about that is when x is greater than 1. And so I can see the piecewise function and recognize that's going to be the bottom one. So for this, I can also use the bottom function, part of the function instead, and I can simply plug in 1 again there, which gives me 4. So the limit does not exist because the limit from the right and the limit from the left are not equal. 1 is not equal to 4. So we're going to move on and talk about what it means to be continuous. there are three things. First of all, a function must exist at that point for it to be continuous. Secondly, the limit has to exist. And thirdly, the function has to be equal to the limit at that point. Let's talk about all three of these in terms of pictures. For the first one, the function has to exist. Notice there's a hole on the red graph, so this would not be continuous because there's a hole there. It does not exist at that point. Whereas on the right, on the green graph, it does exist at that point. Notice you don't need a filled-in hole because the line says that it exists at that point and can be evaluated at that point, so f of a exists. For the second one, the limit has to exist. So if you have something like this, when we looked at that very first problem above, this one would not be continuous because it does not, the limit does not exist there. The right side limit does not exist. Compared to, say, this example where the limit does exist, even though it looks sharp right there, kind of jagged, the limit from the left is equal to the limit from the right, so it exists. And that reminds me, even if you had it defined on the right side like that, the limit would not exist because the limit from the left is not equal to the limit from the right. So condition 2 would not be satisfied on the red graph. For the third condition, they have to be equal. So on here on the red graph, you notice I have a limit and it exists, but it doesn't exist at the same point. Compare that with right here, the limit exists and the function exists, and those two are equal. If you think back to Algebra 1, we even defined this. These three are basically or roughly equivalent to saying if you can trace through that value of a without lifting your pencil, then it is continuous. Look at the three graphs on the right. You can draw those without picking up your pencil. The three graphs on the left, however, you cannot draw without picking up your pencil. The first one because there's a hole there that you would have to lift your pencil to get across. All right, there are two types of discontinuities. One is called a removable discontinuity. That's if f of x can be made continuous just by defining one single value. Look at that green. That's an example of removable discontinuity, and we used to call these holes before. We still sometimes will use those, but we're going to try to get good about using the vocabulary removable discontinuity. If you know there's a hole there, that's a removable discontinuity. In contrast to a non-removable, that's if the limit does not exist. So if the limit doesn't exist, that means that you cannot simply put one point in and make it continuous. So there are two examples of this that just come off the top of my mind. If there's an asymptote, then that is not a removable discontinuity, or rather it's a non-removable discontinuity. Or if the limit from the left and the limit from the right are not equal, that is also an example of a non-removable discontinuity. So how do you find that? Well, what you can do is you can evaluate the limit. Sometimes that means dividing out the numerator and denominator. Sometimes that means that you can look at the graph and simply identify where the hole would be. And so you simply set that value equal to the limit as long as the limit exists, and that's where the hole is. Or that's where the removable discontinuity is. So let's look at this example here. For what values of x is f of x continuous? Well, over here on the left, that part is continuous. So you can say from negative infinity to negative 3. And remember, we're talking about the x values here. Also, it's continuous here in between those two parts, because from negative 3 to 1, this function is continuous. And over here on the right, from 1 to infinity. Those are all the places where this function is continuous. Now, for this next part, we're simply going to evaluate the function, find out the output. We're going to find the limit from the left and the limit from the right. And then we're going to determine the limit, and we're going to say if it's continuous, and if it's not continuous, we're going to determine the type of discontinuity, all from this graph up here. So first of all, the output for the function, if the input is a1, that's c3. I'm going to circle that right here. You see input is a1. Remember the y value is the output, and that's C3 right there. The limit from the left, remember that little minus up there means from the left, that's going to be right down there where the red arrow is. So as you approach A1 from the left, you're getting closer and closer to C1. That means the limit is C1. The limit from the right, remember that's what the plus means, that's going to be where the green arrow is, and notice that we get closer and closer to the value C3. So in this case, the output is equal to the limit from the right, but the limit does not exist because the limit from the left and the right are not equal. Since the limit doesn't exist, it is not continuous. What is the type of discontinuity? Well, since the limit does not exist, it is a non-removable discontinuity because you can't simply change one value and make this a continuous function. There will always be a gap or a jump between C1 and C3. For input A2, that's up there, this is actually going to be a quick one. The output is C6, and notice from the left and the right, they're both going to that same point. So the limit from the left is equal to C6, the limit from the right is C6. That means the limit exists, and since the limit is equal to the output, it's continuous. You could trace over that without lifting your pencil. Since it's continuous, we're not going to answer the last column, so you can just put a slash through that. Now, for the next one, we have a hole here, so it is not actually defined. Now notice we use undefined, you can abbreviate it UND, but you do not want to say it does not exist. Limits do not exist. Values are undefined. Those are different things, so make sure you're using the correct vocabulary in each of those locations. The limit from the left is going to be C4, and the limit from the right is also going to be C4 because they're approaching the same point. So the overall limit exists. However, it is not continuous because the function does not exist at that point. Rather, the function is undefined at that point. So what is the type of discontinuity? Well, if you simply plugged that in, then you would have a continuous function. So it is a removable discontinuity. Remember, a removable discontinuity is just a hole. So you can say, oh, there's just a hole at that point, so it's removable. For the next one, A4, that function is defined. The output is C3. But from the left, the limit from the left is C4, while the limit from the right is C2. So this limit does not exist, therefore it is not continuous. Furthermore, because the limit doesn't exist, it is a non-removable discontinuity. In other words, it's not just a simple hole. There's actually a break or a jump in the graph. For the next one, A5, that function also exists, and the limit from the left and the right also exist, but they're not the same. So the output is C5, but the left and the right limits go to C3. So while the limit is C3, the output is C5. That means it is not continuous. However, this means it's a removable discontinuity because if we simply redefine that point and put it down there at C3, then we would have a continuous function. So it's a hole there, and that's a removable discontinuity. Lastly, we notice that this output and the limit from the left and the right are all the same, so the limit exists, they're all C4, and that means it is continuous. Now, suppose we're not given a graph and we can't use a graphing calculator. How can we calculate these algebraically? Well, what you do is you want to look for the values that make the denominator equal to 0. Then you need to determine if you can divide it out, then it will be a hole or a removable discontinuity. If you cannot divide it out, then it will be a non-removable discontinuity, often a vertical asymptote. So let's do this first one here. First, I want to factor this. I notice a GCF of 3 in the numerator, and I notice a difference of squares, so I get this. The x plus 1, that's in the denominator, so that's going to be our discontinuity, and I'm going to set it equal to 0, which gives us x equals negative 1. But because you can divide that out, that means that discontinuity is going to be a hole. There's a factor in the numerator and the denominator. So, remember, a hole is a removable discontinuity, So this x equals 1 is a removable discontinuity. Compare that with number 2. Notice that we have two different factors in the denominator. We set both equal to 0. So we get x equals 1 and x equals negative 2 are the two discontinuities. But notice that you cannot divide this out because those factors do not exist in the numerator. So these are non-removable discontinuities. And in this case, we know that they're actually vertical asymptotes, which is an example or a type of non-removable discontinuity. For number 3, notice how x appears in the numerator and the denominator, so it's a factor that can be divided out. So when x equals 0, that's going to be a whole or removable discontinuity. However, x plus 1 is a factor that only shows up in the denominator. So x equals negative 1 is going to be a non-removable discontinuity because there's nothing to divide out in the numerator. All right, let's get to this next one. This is a piecewise function. You notice that the instructions say find the discontinuity, so we can actually assume that it is discontinuous here, but I want to show you guys why. For one thing, we have this function. Notice this is the same or similar to number 1, and one of two things is going to happen here. Either this function is going to go along and that other point where it's defined, see when x equals negative 1, the function equals 2, either that value is going to be away from the graph, in which case it's going to be discontinuous or non-continuous, or it's going to show up right on where the hole is, which means it's going to be continuous. So the first thing we want to do is we want to check that out and make sure that that value, the limit, is either the same or different from the function at that point. So let's evaluate the limit of the top part. If we evaluate the limit of the top part, that's going to tell us what the value would be at that hole. So the limit as x approaches negative 1 of 3x squared minus 3 over x plus 1. This limit, we can factor that out, and we can divide out the x plus 1 because we're within the limit. So once we divide that out, we get 3 times x minus 1, and we can just substitute the negative 1 in. We get that the the top part of the piecewise function, the first part, if we could plug in negative 1, we would get negative 6. In other words, the limit as that function gets closer and closer to negative 1 is negative 6. Notice that's not the same as what was defined there. It was defined as 2. So that means that we got the first type, the graph looks more similar to the first type rather than the second type. It does not look like that. So we just found out, what is that discontinuity? Well, it's when x equals negative 1. Because those divide out, however, that means it's going to be a removable discontinuity or a hole. All right, for this last one, I'm going to go ahead and factor it. And I see, the x plus 5 and the x minus 4 are factors that do not divide out. Since they do not divide out, this is going to be a non-removable discontinuity. And in this case, we know those are actually vertical asymptotes. All right. This next one asks us to determine if a function is continuous at x equals 2. Notice x equals 2 is the problem because all of these happen right around 2. We have x less than 2, x equals 2, and x greater than 2. So what we must do is we have to show each part of the definition of a continuous function. What I'm going to do is I'm going to take the limit from the left and the limit from the right and evaluate the function, and we're going to see how those compare. The limit from the left is when x is less than 2. We can simply substitute the 2 in there because there's nothing that we would divide by that would cause a problem. So 3 times 2 minus 2 is 4. For the middle function, that's straightforward. You simply 5, so it doesn't matter what x is, the output is 5. For the bottom part of the function, I'm going to check the limit as x approaches 2 from the right. Since there's no problems dividing, we can simply substitute the 2 in, and we get 4. What you see here is that we get two different values. The limit exists because the limit from the left and the limit from the right are the same. They're both 4, but the function at that point is 5. So it is not continuous, but there's a removable discontinuity because the limit exists. For number 7, we need to show that it is discontinuous at x equals 3, and we're going to justify it by checking each of the 3 conditions for continuity. I'm going to write down all 3 parts of the definition, and you need to have these 3 parts memorized. So I would recommend using flashcards for the 3 parts and studying that until you can recite them. And it would make a great pop quiz. I'll just put it that way, okay? Hint, hint. So, what are the 3 conditions for continuity? The first one is that the function exists. So we want to check that f of 3 exists. It does because it tells us when x equals 3, the function is 4. So check, that exists. The second condition for continuity is that the limit exists. So we're going to check that by evaluating the limit. And notice I can evaluate the limit from both sides at the same time using algebra. I factor out that, and I'm going to divide out the x minus 3. At this point, I can substitute the 3 in there. So we get 3 plus 3 is 6. So the limit exists. That's good. For the third one, though, the limit at that point must be equal to the function at that point. And this is where you run into a problem. You notice the limit is 6, but the function is 4. So it is not continuous because of that. So how should f of 3 be defined to make f of x continuous? Well, simply we need to make f of 3 be equal to 6 instead of 4. That way the limit is equal to the function at that point. Just a reminder, this is the definition of a removable discontinuity, where if you simply redefine one point and you get a continuous function, you have a removable discontinuity. So what we have here, this function f of x, is a removable discontinuity because if we redefine f of 3 to be 6, we now have a continuous function. All right, using g of x, write a piecewise function and call it h of x so that h of x would be continuous at x equals negative 2. So I'm going to start off writing a piecewise function like this. Whoops. There we go. I wrote down the original function there as one part of the piecewise function, and I said, all right, that's going to be our function as long as x is not equal to negative 2. I need to also write a part of the piecewise function for when x is equal to negative 2, and the question is, what should I put there in that blank? Well, what we could do is we can take the limit as x approaches negative 2 of g of x and find out what that limit is, and once we find the limit, that will tell us what the value of the function should be there to make it continuous. Notice a few things here. First of all, this type of problem is an excellent type of problem, but not one you can memorize the steps of. It's just one of a lot of different types of limits problems, which if you understand the way continuity and limits works, then you'll be able to do this problem. That's the way the AEP test works. It does not have a bunch of skills that you have to make sure you do skills 1, 2, and 3. Instead, it will give you open-ended problems like this that make you think about it. So what we're going to do is we're going to practice doing a lot of these kinds of problems. In other words, problems that I don't show you exactly how to do, but I give you all the concepts and all the ways and an understanding of the material, because there's no way to study for the AP test by doing every single possible type of problem. They really seek out problems that make you think and not problems that simply make you compute. So, having said that, what we're going to do here is we're going to take the limit of this. So the limit as x approaches negative 2 of this function, this is going to tell us, let's see here, we can divide out x plus 2 there, and that means I can plug in negative 2. So I plug in negative 2, I get negative 7 over negative 2, also known as 7 halves. That means that the value we were looking for was 7 halves. If we substitute that in there, if that's the part of the function, now the limit is going to be equal to the value of that function at that point. So it will be continuous. Just a reminder, that means that the original function g of x has a removable discontinuity at x equals negative 2. All right, the last one here. Find a so that h will be continuous at x equals 1. That's supposed to be x equals 1, sorry. This is an even better type of problem, showing you how many different kinds of problems that the AP test makers can think up and create, and there's just simply no way to practice all these types of problems. What is this asking for? Overall, this is asking us to create a function or make this function so that it's continuous at x equals -1. And you have to know that continuous means the limit exists, the function exists at that point, and that those two things are equal. For the limit to exist, we need the limit from the left and the limit from the right to be the same, for them to be equal. And the only way for that to happen is if we find the value a where the limit from the left and the limit from the right are equal. So that's what I've written out here. I've written out that the limit from as x approaches -1 from the left is the same as the limit as x approaches -1 from the right. And I filled out those two functions. That's our goal. And what we're going to do is we're going to evaluate it in order to calculate a. Once we have found a, then we're going to check our work on the back end to make sure that this function is continuous. So, first of all, if I evaluate this, I can simply plug in -1 into the x's. The reason I can do that is because there's no dividing by zeros if I plug in -1. So there's going to be no issues if I try plugging -1 into these two functions. So let's go ahead and do that. Notice I'm plugging in for x because that's where the limit, it says the limit as x approaches -1, not as a approaches -1. So I plug those in, and let's just evaluate this. Now we have a linear equation. We can actually solve for a here, and I solve for a and I get a equals 3/2. So supposedly if I put 3/2 in there for a, and for this one and that a, then these two sides of the function are going to line up, and you can picture it as it will be a function where you can sketch it without lifting up your pencil. So let's check this by going back and testing out the three conditions that need to be met for continuity. The first condition is the function must exist at that point. So we check it here, and sure enough, the function exists at h of -1. It's equal to 5/2, so the function exists there. For the second one, we have to check to make sure the limit exists. Now I'm going to calculate the limit here. Really what I should be doing is calculating the limit from the left and from the right, but we just kind of did that here. And so if I just pick one of those, I can make sure that they both exist. And so I'm going to simply plug in the value of the top value. The other thing I can do is kind of sneaky and cheating here, not really cheating, but just sneaky, is that since this is an x is greater than or equal to 1, I kind of already checked that the limit from the right exists up here. Because if I took the limit from the right, I would get that exact value, the top one. So I really want to make sure, mathematically, I want to make sure that my limit from the left also exists. So I'm plugging this in. I plug in -1 everywhere there's an x, and I have my a plugged in, that's 3/2. And when I calculate this, I get 5/2. Great, so the limit exists. The last thing I want to do is I want to make sure the limit is equal to the value of the function at that point. Is it? Well, yes, they're both 5/2, so check. The limit exists. And therefore, h of x is continuous, so we found out that as long as a is 3/2, that is the value that will make h continuous at x equals -1. Thank you for watching.